Hi, my name is Alexandra Koval-Reeves, and I'm going to start by introducing you to Team 3's device for DP4. Our device, BioGrip, is a glove containing motorized prosthetic fingers that are able to complete a gripping motion with minimal joint movement from the user's fingers. Our group's client, Miss Lou, is a full-time student who has an autoimmune disorder, which causes her to experience a variety of symptoms including joint pain, swelling, and a limited range of motion. Although this applies to many of her joints, it's concentrated mainly in her knuckles and wrists. We designed this product for our client, who needed a way to complete fine motor skill-related tasks without the pain and limitation caused by her autoimmune disorder. We wanted to design a product that would integrate seamlessly into her everyday life by giving her the ability to independently complete tasks, such as holding a pencil to take notes or brushing her teeth, without any of the pain that she previously experienced. As a full-time student who is unable to predict which days she will experience a higher degree of limitation due to her joint stiffness, our group knew we had to create an easy-to-use device that Miss Lou could use whenever required. Our group designed a list of customer requirements comprised of objectives, constraints, and functions, some of which are listed on the screen, and we used these to guide our design process. We focused on making the device easy to operate, portable, and time efficient so that Miss Lou would be able to use it independently to complete actions. We also ensured the device required minimal user interaction, did not cause pain, and allowed Miss Lou to independently complete fine motor tasks while remaining comfortable. This addressed our need statement and gives Miss Lou the ability to hold a pencil and complete other similar tasks independently with minimal pain or discomfort.
My name is Nicholas Carbonera, and I will be talking to you about our proposed design solution, BioGrip. In order to accomplish our need statement, our group designed BioGrip, a user-controlled motorized finger prosthetic. BioGrip consists of 4 prosthetic fingers, the index, middle, and ring fingers, which will be referred to as the central fingers, and a thumb. The central fingers are all controlled by the same drive shaft, which is powered by a servo motor. The design of the thumb prosthetic is similar, however its drive shaft only controls the one prosthetic. Incorporated into each prosthetic finger is a slit through which a string will run from the tip of the finger, ultimately attaching to the drive shaft. Consequently, as the drive shaft rotates, the string will wind, causing the joints of the fingers to bend, as the prosthetic finger is made from thermoplastic polyethylene, which is a flexible material. The BioGrip consists of 4 input sensors, more specifically, flex sensors, which are embedded in each finger slot of the glove portion of BioGrip, except for the pinky. These flex sensors can detect minimal user finger flexion, and a pre-programmed response will be executed depending on which finger is flexed. BioGrip consists of the following commands. When the thumb is flexed, the thumb prosthetic finger undergoes controlled close. When the index finger is flexed, the 3 center prosthetics undergo controlled close. When the middle finger is flexed, the complete opening of the thumb prosthetic occurs. And finally, when the ring finger is flexed, complete opening of the 3 center prosthetics occur. Controlled close means if the user's finger is flexed, the prosthetic will close, and once the finger returns to a relaxed state, the finger will stop. As mentioned previously, we believe that the product we designed should fulfill various customer requirements, such as minimal user interaction, and as well, aids Miss Lou in the independent completion of fine motor skill tasks. The BioGrip seamlessly accomplishes both requirements. With the use of flex sensors, Miss Lou is not required to move her fingers greatly to control the device. In addition, due to the various control commands, BioGrip allows for a variety of tasks to be completed independently, such as holding a pencil or holding onto a water bottle. We believe that BioGrip is an ideal device that Miss Lou can incorporate into her day-to-day activities and restores some of her independence and freedom that her disease has stolen from her.
My name is Saraf Rida, and I will be talking about the preliminary prototype. The goal of the preliminary prototype was to aid in the description of our idea, thereby having zero functionality. The initial idea was for the device to imitate the movement of her actual fingers, but amplify the movement through the prosthetic fingers. For instance, a certain degree of movement of her index finger would cause the index prosthetic finger to be fully curled. Ideally, the device would be very versatile and could assist with a variety of tasks, such as opening doors, holding a pencil, opening her water bottle, etc. The prototype consists of a cotton glove, which is how she wears the device, The carbon fingers represent the prosthetic fingers, and the neon felt represents the flex sensors. From this preliminary prototype, we learned new information which resulted in many alterations for the next prototype. One major problem was the material of the glove. Cotton is not a breathable material, meaning it would result in an accumulation of sweat, leading to further skin irritation. Through discussion, we realized many problems would arise with using the device for different actions that all require variation in force. For instance, it would be unnecessary for her to carry heavy objects, which could result in technical problems with the device destructing. Additionally, we realized that not all fingers are necessary for most motions like the pinky finger. Therefore, the main functions of the device have been narrowed down to simple gripping motions, such as holding a pencil or a utensil. One modification was the material of the glove. It was changed to polyviscose from cotton to mitigate skin irritations. A major alteration was the control of the prosthetic fingers. Initially, we had each prosthetic finger be able to move independently. Accordingly, we felt the device would be much more useful with assigning each finger a specific hand position.
My name is Daniel Samak, and I'll be talking about the future of BioGrip. While the BioGrip greatly empowers our user, there are some key points of improvement that should be made. Our current model uses a Raspberry Pi Zero, a motor driver, an analog to digital converter to control the device, a program printed circuit board containing the required microcontroller and electrical components would greatly decrease the size of the control unit located on the back of the glove. This results in a slimmer product and allows room for a greater capacity battery to be implemented. The PCB would first be designed and printed using computer software. The microcontroller would then be programmed, and then the components would be assembled into the device, similarly to the current build process. Higher precision motion is an aspect that must greatly be considered for the successful future of BioGrip. This will allow users to achieve a greater variety of tasks, such as opening a water bottle. We plan to implement microcontrollers into each prosthetic finger joint, resulting in more controlled movements capable of effectively achieving fine motor skill movements. We will also experiment with using EMG sensors to detect user input, as that allows detection of a command from each of the user's finger joints, allowing user control of each prosthetic joint. If the user's joints are swollen, an EMG sensor can detect electrical signals and elicit a response even if the finger does not physically move, a feature unachievable with the currently implemented flex sensors. After these adjustments are made, we would provide Ms. Lu with the updated BioGrip to ensure that our product enables her to complete fine motor skill actions with minimal joint movements in accordance to our needs statement. We intend on improving other aspects of the design, such as water resistance and the material of the glove and prosthetics. However, user feedback is first required.